We already know how to handle some integration problems where the integrand is powers of sines and cosines.
For example, I can anti-differentiate sine to an odd power.
How? By trading in all but one of those sines for cosines.
Let's make this really concrete. Instead of talking about an odd power, let's just make it 17. Can I anti-differentiate sine to the 17th power? Yeah, I can rewrite this problem as sine of x times sine squared x to the 8th power, because sine squared to the 8th power gives me 16 copies of sine times another sine gives me 17 copies of sine. Now I can trade sine squared for some cosines, right? Sine squared is 1 minus cosine squared to the 8th power. So if I can do this anti-differentiation problem, all I need to do is to do this anti-differentiation problem.
And I can do that with a substitution.
So make the substitution u equals cosine x, and in that case du is minus sine x dx. Now maybe you're complaining you don't see a minus sign, you only see sine, but I'll just put a pair of canceling minus signs there. Now I see a minus sine x dx, so I've got a du, and the rest I can write in terms of u. Specifically, this becomes negative the antiderivative of 1 minus u squared to the 8th power du is what's left over, and this is an anti-differentiation problem that I can do. I mean, it's a little bit annoying because I guess I want to expand this thing out to find an antiderivative of this, but I can do it.
But what if instead I'd had an even power of sine?
Like maybe I want to anti-differentiate sine to the 4th power, right? So this is not an odd power, but an even power.
Ah, that's harder. I can't trade in all of my sines for cosines because I need just one left over to make the substitution work.
Instead, I'll use an identity, the half-angle formula. It lets me replace sine squared of x by 1 minus cosine of 2x over 2, and it lets me replace cosine squared of x by 1 plus cosine 2x over 2.
How do those help?
Well, I can rewrite this integral as the integral of sine squared squared, and now I can use this half-angle identity. This is the same as the integral, well, what's sine squared? Sine squared is 1 minus cosine 2x over 2, right? These are equal, and still have to square that dx.
Now I expand.
So I get this is the same as integrating, well, the cosine 2x over 2 term squared is cosine squared of 2x over 4. And then there's a cross term, the 1/2 times minus cosine 2x over 2, and there's 2 of those. So I'll end up getting minus 1/2 cosine 2x, and there's the 1/2 term squared, which is plus 1/4. So I just have to do this integration problem.
I can split that into 3 integrals.
So this gives me the integral of cosine squared 2x over 4 dx minus the integral of cosine 2x over 2 dx plus the integral of 1/4 dx. Now the second and third integration problem I can do, I'm just going to copy down this one again, the integral of cosine squared 2x over 4 dx. This here, well, I could do this by making a substitution, u equals 2x, say, and then I'll get that this is sine of 2x divided by 4, and if I integrate 1/4, I get 1/4 x.
What about that first one? How do I integrate cosine squared?
So to handle this, I can repeat the trick with the half-angle identity, but I'm looking at integrating cosine squared 2x, so I'll replace x by 2x, and that'll turn this into a 4x. So I can use this identity.
How does that go?
Well, I get, instead of this, the integral of 1 plus cosine 4x, and instead of over 4, it's now over 8, and then I'll just copy down these things again, sine 2x over 4 plus 1/4 x.
Now I can put it all together.
So I want to anti-differentiate 1/8, and I get 1/8 x, and then I want to anti-differentiate cosine 4x over 8, and I get sine of 4x over 32. And then I'll include the rest. So I'll subtract sine of 2x over 4. I'll add a quarter x, and I'll add some constant. And I could combine the 1/4 x and the 1/8 x, so I could write this as 3/8 x plus sine of 4x over 32 minus sine of 2x over 4 plus c.
I should say that in some cases you can get away doing a bit less work.
So I'm going to calculate the integral from 0 to pi of sine to the 4th. And I'll again start the same way, right? I'm going to integrate from 0 to pi, and I'll write this as sine squared squared, just so I can see how the half angle formula is going to help me. All right, now I'll use the half angle formula. This is the integral from 0 to pi of 1 minus cosine 2x over 2 squared. But now what do I want to do? I'll expand that out again. So this is the integral from 0 to pi of 1/4 minus, the cross term is 1/2 cosine 2x, and then plus the cosine term squared, cosine squared 2x over 4. But now there's a little trick. I'm integrating from 0 to pi cosine, right? I'm integrating cosine over an entire period, and that ends up being 0. So I can just throw this whole term away, and I can keep on going. I can also use the half angle formula here. So this is the integral from 0 to pi of, well, I've still got the 1/4 plus, and then what does this become by the half angle formula? This is 1 plus, and instead of 2x, it's cosine 4x over 8. But now again, if I integrate cosine 4x, x going from 0 to pi, that's integrating cosine over 2 complete periods. That ends up canceling, so I can just throw that term away. And all I'm really integrating now is 1/4 plus 1/8. Well, that's 3/8, but I'm integrating over an interval of length pi. So this definite integral is 3/8 pi.
This turns out to be not so bad.
So yeah, I'm getting an answer of 3/8 pi, but that's not really the point, right? The cool thing about setting this up as a definite integral is really just how easy it is to do the calculation, since I can throw away some terms along the way that I know would integrate to 0.